Hi, everyone. Thanks for joining the second in our Go with the Flow expert webinar series. We're just going to wait a couple minutes to allow some people to come in to the webinar. So just be patient for a couple minutes and then we'll get started. Thank you very much. Hi, everyone. Thanks for joining the second in our Go with the Flow webinar series. I'm just going to wait for one more minute here to get started, allow a few more people to come into the webcast. So hello, everyone. Thanks for joining the second in our Go with the Flow expert webinar series. Today, we have Andres Martinez, postdoctoral scientist at Roche in the downstream processing and real-time monitoring group. I wanted to just give a quick introduction to the Go with the Flow series. This is the second in the series. The first was on dynamic binding capacity. If you register, that's available on demand now. All these series will be available on demand after they've been completed. Every Tuesday at this time, 8 a.m., we'll have a new topic discussing the FlowVPE and VPX. Next week will be UFDF, and the week after will be drug product operations. So please join as many as you can. The final panelist discussion will be where we have our experts along with our CEO, Tony Hunt, to moderate a question and answer session with the experts. So please join that as well. And without further ado, here's Andres Martinez to talk about his work with the FlowVPE in combination with MALS for real-time molecular weight quantitation. So thank you very much for joining us, Andres, and the floor is yours.
Thank you very much, Ramsey, for that introduction and for the invitation. Okay, so let's start. My name is Andres Martinez, and I'll be talking about the integration of FlowVPE and MALS for the real-time measurement of molecular weight. So I would like first to start with a small background of why we're doing this. So here we have a very simple diagram of a unit operation. So in the center, we have the process itself, and it has several inputs. We have the process parameters, we have the raw materials, and we have some inherent variability on the process. This can come from the material itself, from the equipment. For example, chromatographic columns change over time. They can lose their binding capacity. And other variability can be the environmental conditions or something as simple as the buffer preparation, which usually has a range that's accepted. So because of this variability, the processes are designed to deal with it by sacrificing a little bit of yield to always deliver the target quality. So you usually have a process with safe, even though non-optimal process parameters, so that you always meet your quality attributes. These quality attributes are usually measured in an offline manner, either by taking samples during the process to see how it compares against your model and your process design, or by taking samples of your final product, which can be relevant for release. What both of them have in common is that usually you give them to maybe another section of your organization, even to other building, and you have to wait until they are done with the analytics so that you can see how your process went actually. A lot of times this can mean that you have data for your batch after the entire campaign is gone. So you are not able to take any fast decisions with it, and it would be too late to notice any kind of deviation of the process or some unsatisfactory quality attribute. The idea of using process analytical technology is to bring the analytics closer to the process itself. With this, you can, for example, use the information for an adaptive process control. In general, though, you can use this better process understanding to improve your modeling or to support your process development. The quality attribute on which this work is focusing is the high molecular weight species. These are a key product-related impurity since they can generate immunogenicity reactions on patients and are a very important quality attribute. Usually these, as high molecular weight species are created, the molecular weight of the stream increases due to the aggregation. And what we achieved, what we wanted to achieve, was to measure this average molecular weight by taking a look at the light scattering. We based on the Rayleigh theory, which says that the light scattering is proportional to the molecular weight of species and to the concentration. So here we see a very simple diagram of experimental equipment. We have the volume V with the species that we are studying, and a laser is shined into it, and at a specific angle, we can measure the amount of scattered signal, of scattered light, which is being scattered by the species in the volume. So in order to find the molecular weight, we use this scattered light of the equipment, but we also need the concentration of our species in the volume. And this is where the FlowVPE comes in. So usually this light scattering technology is used often for analytical purposes, in which you have a relatively diluted sample. So you can get away with using your fixed path length UV sensor, for example, in your ECTA or conventional chromatography setup. However, if you want to use this approach for a more process relevant conditions, you have to be able to measure much higher concentrations. So we wanted to be closer to these process conditions. That's what we took a look at the FlowVPE. And another factor was the data connectivity. Our objective was to have this data as fast as possible, ideally every second. And so the data connectivity and getting the data from the FlowVPE integrated with the data of the MALS was really important. One of the goals of our work was to use the real-time molecular weight for process control. This has already been done in the literature. They controlled a chromatography step based on a trigger, which is based on the average molecular weight. and they started and stopped the pooling of the chromatographic process. In the literature, however, they were able to use a relatively diluted sample. So they used the ECTA UV sensor, which for our case would be saturated. So they assume a type of HMB species, a dimer, and they define the molecular weight average trigger, which would correspond to a specific amount of percentage of HMBs. We wanted to do this using a standard antibody, which had a molecular weight of about 148 kilodalton. And we, as I said before, we wanted to do it on more process-relevant conditions. We did this using two setups. The first one with a focus on the process control of the chromatography, and the second one to showcase that we could use the real-time molecular weight measurement to support the process development. So I start with the first one. Here we can see the chromatogram of the process, and we see the traditional sensors. So we have the UV absorption, the pH, and the conductivity. The region of interest is here marked by the green square. And so the goal of this process is to separate the HMVs from the monomers. And using these sensors is really hard to make any kind of insight into the process. You could only maybe do it after your offline analytics. Now, if we take a look at the expanded sensors using the FlowVPE and the MALS combined, we can see that first of all, the concentration of using the FlowVPE is stable as we expected, but we can see a very unexpected increment of the molecular weight. In the first part, we have a molecular weight of 150 kilodalton, which is what we would expect. And what we wanted to see, just as in the literature, was a really continuous and slow increment of the average molecular weight. However, we see this huge spike in the molecular weight, and then we started asking ourselves what can be behind it. So just to repeat it, we saw this in real time. So we didn't have to wait until offline analytics, but as the column was running, we could see that there was something unexpected going on. We checked these measurements with offline HPLC measurements, and we could conclude that the observations of the increased high molecular weights were being caused by specific type of HMB, which was a problem with the feedstock. Now, usually you would only see this kind of problem well after the batch is done. However, in this point, we were able to see it as it was happening. And depending on the process understanding that you already have, you can make decisions based on this real-time information. For example, you could decide to stop the batch, maybe save some feedstock, or maybe you could get more hints on what could be. Maybe your column is degraded, or maybe there is a problem with your buffers. But the bottom line is that you know more about your process, and you know more about what's going on. So we started with the troubleshooting faster than usual. So we were able to pinpoint the problem to the feedstock. So we repeated the chromatography with similar conditions, and this is what we got. The molecular weight is in blue, and we can see what we expected, which is the molecular weight is starting at around 150 kilodalton and very slowly increasing as the amount of HMVs increase in the process stream. We checked this with offline analytics in HPLC, and we could see a good agreement between both measurements. So the goal with this first chromatographic setup was to showcase that we could use the combination of the FlowVPE and the MALS to control a chromatographic setup. And this is how our control algorithm looks like. As I mentioned before, we have the MALS, which gives us the scattered light, and we have the FlowVPE, which gives us the concentration. We read both of them using a digital converter, and we can use this information in a program, in a pre-written script, in which we can use this data as we want to. And once the molecular weight goes above a specific threshold, which was predefined, we can send signals directly to the ECTA, maybe to go to the next method block or to change the flow rate or evolve as we see fit. And so this enables us this gives us more capabilities to achieve an adaptive process. Overall, we got a very fast insight into the process, which enable us to get a little bit more of yield out of the unit operation while still achieving the quality control that we want to have. And in the cases in which we have something going on that we don't know what it is, we know faster that there's something unexpected going on. Now to the second chromatography setup. The focus of this was to show that we can support the process development with real-time molecular weight measurements. The goal of this chromatography step was to separate the monomer and the HMVs into two pools, the first one being the monomer and the second one being the HMVs. So how the process development usually goes is that you have a chromatography at different parameters, your pH, your conductivity, your salt species, etc. And you have a matrix of parameters, and you carry out your chromatography, and you analyze your pools or you analyze your fractions by sending them to the offline analytics. So you have to collect them, you send them, and you wait for the analysis, and maybe a couple of weeks later, you get the results back. And then you can plan for the new experiments. Since the defining quality attribute of this chromatography was the HMV content as well, we applied the real-time molecular weight measurement to support the process, to show that we can support the process development. And this slide has a lot of information, so I would like to start with the left graph. So here we see the data that we have available in real time. We have the concentration from the FlowVPE, and we have the real-time molecular weight from the integrated sensors. The green points are the confirmation offline analytics. So this was a good parameter set. Then that means that this is what we wanted to achieve. And the real-time molecular weight measurement can support this, in which you get more information on each pool. So if we take a look at the first one, we can see that the molecular weight is around 150. It's a bit lower, maybe because low molecular weights are there, or due to the maybe an inexactitude of the measurement. And if we look at the second pool, we can see that the molecular weight there is much higher than the first one. So we can safely assume that we have much more HMVs here in comparison to the first one. If we compare these results of the good parameters with the worst case parameters, we can see that for the monomer pool, we have a slightly higher molecular weight, which can indicate that we have unwanted HMVs there. But what's really striking is that for the HMV pool, we have a much lower molecular weight. What this means is that we have here a higher amount of monomer, which is the opposite of what we want. So this information was available in real time. That means that together with the other parameters, the pH, the conductivity, and etc., you can add them to your parameter matrix, and you can avoid, at least during the initial condition screening, the time-consuming offline analytics. So you can start your screening and on using these expanded sensors. And even though you get so you can get a faster initial screening using the real-time molecular weight, maybe as you go into a more smaller parameter space, you might not be able to use it because the changes of the quality attributes of the chromatography, they might be a bit smaller. So the higher sensitivity of the offline analytics are still necessary, definitely. But the real-time molecular weight measurement is just another tool that you can use, at least for the initial condition screening. Also, as shown for the process control experiment, it is possible to read this information just like any other parameter. So you can program something, a program in Python or any other language, with which you can just set up your ECTA and tell it what to do, what to look for, and just let it run for a week and maybe walk off. And in the end, you're going to get an approximation of the parameter space, which can give you the an estimate of the amount of uv-vis that you get out of the process, which can save time and resources. So I'm coming to the conclusions of my presentation. If we were able to show that the FlowVPE can be integrated to the MALS for the real-time molecular weight measurement, this integration was adequate for fast changing concentrations characteristic of chromatography setups. We also noticed that the data connectivity is really important and is something that sometimes you don't think at first by focusing too much on the equipment or on the measurement itself, but the data connectivity is really important if you need to have very fast analytics. We use analog signals mostly in this work, but we got to play with the FlowVPX and other instruments with OPC functionality. And we noticed that these are, we prefer them because you can just ignore some problems with analog signals like electric noise or cable shielding or voltage offsets. So in general, we were able to show that we can support the process development and that we can generate another tool for the process control by coupling the FlowVPE to the MALS. And I thank you very much for your attention. And if there are any questions, I would be happy to answer them.
Thanks, Andres, for this really great presentation. So for everyone on the line, if you'd like to type in a question to the questions box, we can have Andres answer it. I personally have a number of questions. This is a relatively new application from my perspective as well. So I'd like to ask and maybe kick it off with a couple. So Andres, I noticed on your graph, you had the MALS signal on one of the first graphs that corresponded to what looked to be a flat signal from the FlowVPE, but I think I noticed some kind of jump in the signal on the FlowVPE as well that corresponded to the increase in the high molecular weight. Did you see that, or was there a correspondence of the UV signal to the changing to the high molecular weight signal from the MALS?
Yes, there was a change, but it was really small. Maybe let me take a look at this slide that it was on. Oops.
Yeah, it was kind of in one of the first data sets that you showed where the FlowVPE was a flat signal. Yeah, it's there.
Yeah. So there is an increase in the concentration of what's coming out of the column. It's a really small increase, so it's really hard to conclude anything out of it. It's only when you couple that to the light scattering that you can see what it really means. And what it meant was that there were some HMV species coming out of the column.
Yeah, so I mention it because I know from some previous work by Jürgen Hubik at KIT, we looked at spectral measurements for the FlowVPE, and they had some kind of similar conclusions. So that's why I was curious if maybe there was some correlation there, and maybe there's some more research we could do in that area. So a bunch of questions are popping in here. Was this purely used in development? Do you believe it could be useful in a production setting?
So I think so it was mainly used during, or the goal was to showcase that it could be used for both of them. For the development, I think the use case is easier because you don't have to be as exact for this application, at least during the initial screening, because you can just get a feeling to what amount of HMVs you have in your pool. For the manufacturing, the defining factor is that HMVs are not a single species. You could use this, in my opinion, for manufacturing if you're really certain what you have. For example, in the literature, here the authors assumed that they only had dimers. So if you only have dimers, this equation is pretty simple. So you have two species here, and you can find the other one pretty straightforward. However, depending on your molecule, it can be that you not only have dimers, but you have trimers. Maybe you have weird aggregates, so you get more and more factors here. So you have more variables, but you have the same amount of information. So I would say that it really depends on what you have. If it's safe to assume that you have only dimers or trimers or whatever, or if the family of the HMVs is really constant, then it should be possible to use it in a very robust manner. But if it's going to be changing, it's just going to be hard to be certain if you have a lot of dimers or if you have just a couple of very huge aggregates that really skew your signal.
And maybe I could just take that question one step further, because it was actually the same as my question. What would you see the advantage of this technique in a production environment? If it's possible to use it for something that's a standard molecule that has only a certain type of high molecular weight impurity, what do you believe the advantage could be there?
So if you know what kind of HMVs you have, then you would get something like inline real-time measurement of percentage of HMVs. So you could use this algorithm to control your chromatography. So you wouldn't be restricted to the very safe process design, but you could build the variability of your feedstock into the process. In that way, it wouldn't matter that much if your raw material has, for example, 2% HMVs today, and for any reason in 2 years it has maybe double as much. Your instruments are going to check what's coming out of the column and your algorithm is going to guarantee that you reach your quality goal while getting as much yield as possible. So for any chromatography step in which the defining quality attribute are the HMVs, if you know what kind of HMVs you have, then this coupling could be useful.
Great. So we have a number of other questions, so let me try to get through them. What's the traditional use of MALS by itself? Can you give an indication of high molecular weight level, maybe just a relative measurement using MALS?
So I'm not an expert on MALS on its own. I think you always need a concentration measurement to get the molecular weight of a sample. What you can do with MALS, I hope I'm not wrong, but usually the MALS instruments, they have several angles. So here I just focus on the case with only one angle, on the simple case, but you can imagine that the equipment have multiple angles here. And I think you are able to measure the hydrodynamic radius of your molecule by just looking at the difference between the light scattering at different angles without taking a look at the concentration.
I see. So actually that answers the next question, I think, but I'll ask the second half of it at least. Did you compare the multi-angle to single angle, or was it just a single angle, just to confirm?
We focus mostly on the single angle because we wanted to keep it simple at the start. So we could see some coincidence, for example, here as the molecular weight increased, we could also see that the information from the other angles also told us that the HMVs were getting bigger. So, but we didn't want to use that here for the real-time molecular weight because it would be more complicated from the data point. But yeah, we also took a look at that.
Great. There's a comment here from the line. It turns out someone who has some experience in working on this mentioned that the increase in the A280 might be connected to a change in the spectrum due to the HMW content, and that's something I alluded to earlier. The work in Jürgen Hubbeck's group at KIT years ago has some information regarding that in the literature that we could look into in the future. And then there's another question. Was A2 self-association taken into consideration for these experiments? Was an A2 value determined?
Yes, what we did was we made a dilution series from very, very diluted protein up to the process concentrations. And we saw that the A2 didn't play that big of a role. So we found the A2 empirically, so to just feed it to so when we pushed, well, better said, when we measured monomer that we knew was very, very pure monomer, we compared the theoretical molecular weight to the measured molecular weight, and they were really close to each other. So the A2 was quite small, and on top of that, we diluted these samples in a wide range, and we could see that the concentration didn't have that huge of an impact on the light scattering. So it confirmed that the A2 wasn't that big.
Okay, another question is, what are the main issues you came across using the setup with the MALS and the FlowVPE?
So maybe one small obstacle is during the transition period. For example, here you can see when things are changing fast, even a time delay of a couple of seconds between the instruments can make a big difference. So the focus of this process is not on the transition part, so that's fine. We know that it doesn't affect the control algorithm, but if that was the case, then that could be a problem. The other thing is that maybe the MALS is really sensitive to whatever is coming out of the column. So you have to be really sure that your column has been cleaned and there's nothing weird coming out of it. So you have to clean it maybe a couple of hours before, just to be certain that your stream is quite clean and doesn't have any particulate matter there. But in general, once we were able to couple the information from both sensors and we solved the physical equations, it was quite quite easy to use.
Great. So this was actually a question I was going to ask. What challenges did you face for flow through versus bind in the loop on the MALS or FlowVPE? So I guess the different modes of operation of the chromatography, what kind of challenges did you see for those?
So the the biggest challenge, it most likely is the volume delay between both sensors. Since you have some dispersion between both of them, and you have to take into account the time delay caused due to the volume delay, you have to program that into your equations. And of course, the faster your chromatography is changing, the bigger the influence of these delays are. So I would say that's the biggest one. And in general, I think the biggest one is just being certain of what's coming out in respect of the HMVs. As I mentioned before, the HMVs is not only one species, but a family. So I think that's the biggest point. You have to be sure how your HMVs look like. And maybe you can do that because you know your process so well and it's so well characterized that you can safely assume what's coming out. But still, you have to do that before using the MALS for manufacturing process control.
I see. So then another question is the software used to calculate and display molecular weight, is that commercially available or is that something that you developed yourself?
It was all in-house.
Okay. You care to elaborate on that a little bit? I mean, was it something that was, I guess I would like to understand from my perspective, like how much effort was it to develop that kind of software? You know, was it easy, hard? Did you use sort of off the shelf packages? Maybe some, more details there.
So we wrote it ourselves, basically. We just read the analog signals from both instruments and coupled them to fit them into a computer using quite normal off-the-shelf electronics, and just use them into a script with a very common language. But like the language doesn't even matter. You can use Python, you can use MATLAB, you can use Visual Basic maybe. It doesn't matter, but it's something relatively straightforward.
Great. Yeah, that's very interesting. So then another question, what were the flow rates used for these experiments? Or maybe also I would add maybe what the column size or something like that.
So they were all small columns. So these weren't done on larger ones. These were like a proof of concept. So these were done on smaller than couple of centimeter diameter columns.
And we have a comment from one of our friends at Wyatt, who's on the line. He said, real-time MALS software is commercially available from Wyatt. So you can, I guess, reach out to them as well if you need some information on the MALS. you know, so I guess there must be some commercially available stuff for that. So I think the questions have kind of slowed down. I'll give one more second if there's any more questions. We still have some time. And if not, we can then close the call. Here's one that popped in. Would the delay timing be less of an issue as you go higher in flow rate?
Yes, if you have the so the time delay is the volume delay between the sensors in comparison to the flow rate. But usually your flow rate is already defined by your chromatography process. So the idea is to diminish the volume delay as much as possible. But yeah, I mean, if you run it faster, then the time between the sensor is going to be smaller.
Yep, makes perfect sense. Okay, so if there's not more, I just want to say thanks again. This is a really interesting application. I hope to see more work on this kind of stuff in the future. Thanks again for coming. And oh, what popped one more here? Hold on. Could this approach be extended to larger biomolecules such as viral vectors or exosomes? Does the transition from the Rayleigh regime to the Mie scattering regime pose significant challenges?
Unfortunately, I'm not sure.
Maybe our friend from Wyatt can maybe answer some of that. And I think I can maybe unmute him. Hold on. So he says, yes, it's incorporated into the RT-MALS software. So I'm not an expert on that either. But it sounds like, you know, for those other exosomes or viral vectors, maybe we should have a conversation with Wyatt. We can try to recreate this kind of work with the FlowVPE and the MALS for that. So yeah, that's really great. Thanks all for the questions and the interaction. It's been really helpful. And then just another reminder, next week on Tuesday, 8 a.m. Pacific, we'll do the UFDF, FlowVPE VPX for UFDF. And then we'll also do the drug product one the week after, and then the panel discussion with our esteemed CEO, Tony Hunt, where we can interact with the experts and talk to them in a little bit more detail. So again, thanks for coming. Thanks for the presentation, and I hope to hear from everyone next week.
Thank you.